Hi everyone, I'm going to talk about our project Chronic Kidney Disease Prediction. Our team is Anne, Alista, Grace, and Wilfred. Let's dive in. Chronic kidney disease affects over 10% of the population, which would be over 800 million individuals. With the growing popularity of AI, an investigation of AI applications to healthcare should be conducted. Our goal is to use various machine learning techniques to classify if a patient has chronic kidney disease or not, based on clinical health parameters. The dataset we are utilizing was sourced from Keiko, originally obtained from the UCI Machine Learning Repository. It is licensed under a Creative Commons Attributes 4.0 International License. The dataset contains 24 features and 400 records. There are 14 numerical data types and 10 categorical data types. The binary response variable classifies instance as either have chronic kidney disease or not have chronic kidney disease. The categorical features contain misspelled labels, as observed in the MCAD and classification. The distribution of the numerical feature reveals non-normal distributions, especially in features with discrete values such as AL, SU, and SG. Additionally, many numerical features exhibit varying ranges. To address these issues, we will conduct feature scaling before performing PCA. After data cleaning, addressing missing value is our next step. We utilize an iterative imputer for numerical features and an imputer for categorical features. Observing the statistical parameters, we find that imputation does not significantly alter the dataset overall characteristic. Statistical parameters remain similar between the raw and imputed dataset. So when we check out those VIF value, it was pretty clear that there was some multicollinearity going on. Some of the features have pretty high VIFs, which means they are strongly correlated with each other. We noticed that SG and SOD were standing out, suggesting high correlations between these features and possibly indicating physiological relationships such as those between sugar and glucose level or hemoglobin and red blood cell count. Scaling techniques and PCA have been implemented to help ease those multicollinearity concerns. We also turn to models like lasso regression, tree, and random forest that can automatically select features and might be able to remove features that have a high level of multicollinearity. Principal component analysis help us minimize computation resource while maximizing model accuracy. Several models suffer from the curse of dimensionality, and PCA can help with that by lowering the number of dimensions while retaining entropy. The elbow method would have helped us use one principal component. However, less than 60% of variance is captured with just one component. Instead, to capture approximately 90% of variance, we decided to use 7 principal components. We trained the logistic regression model with L2 regularization, so we decided to train the model with both full scale and PCA reduced training sets. We use cross-validation to help select the best parameters. However, it does not improve accuracy. The model trained on the scale dataset yields higher accuracy than the model trained on the PCA dataset. This seems to imply that the regularization can optimize the feature selection. The lasso regression yields the same performance as the logistic regression. Since both models use L1 and L2 regularization, it shows here that there are only 5 features with a coefficient magnitude of more than 1, and more than half of the features are eliminated. Both the train and test accuracy remain the same after applying PCA, indicating that the dimensionality reduction by PCA did not impact the performance of the Gaussian naive Bayes classifier. This suggests that the original feature space and the reduced feature space capture similar discriminatory information, enabling the classifier to perform effectively even with fewer features. Overall, the Gaussian naive-Bayes model demonstrates consistent and high accuracy on both the training and test dataset, indicating it is quite robust and can be generalized. The next model we investigated was K-nearest neighbors. This model looked at the K closest data points and used those to make the prediction. We first did this on the full-scale dataset and used grid search from 3 to 15 neighbors and uniform or linear weighting of the K-nearest neighbor. The optimum parameters were 7 neighbors and a uniform weight. This gave a test accuracy of 96%. We did the same thing on the PCA-reduced dataset. This gave a model that used 5 neighbors and uniform weight. However, test accuracy was reduced. This is unexpected since with 24 features, we thought PCA would help with the curse of dimensionality that seemed to plague distance-based model like KNN. Next, we use a support vector machine classifier. Once again, we did a grid search. This time, the parameters were the regularization parameter C, ranging from 0.01 to 2, and the kernel type either a linear or radial basis function kernel. On the full dataset, we have regularization parameter of 0.03 and radial basis function kernel. This gave a test accuracy of 96.25%. On the PCA-reduced dataset, the kernel function was changed to a linear kernel. This gave a test accuracy of 95%. Once again, PCA did not improve the model performance, which is unexpected since the SVC model, just like the KNN model, also has an issue with the curse of dimensionality. Let's move on to decision tree classifier. The feature importance measured by the Gini index show that 6 features are used to build the decision tree. While achieving a good test accuracy of 97.5%, the model's perfect training accuracy and unrestricted parameters resulting from the grid search hint at the potential overfitting. To tackle this, we will explore random forest, which combines multiple decision trees and could offer better performance and generalization than a single tree model. For random forest model, we only tune 4 parameters to leverage the adaptability of the random forest, utilizing techniques like bootstrapping and out-of-bag sampling. No random state setting to preserve this intrinsic randomness of the construction of the tree. We compute accuracy by averaging the result of 100 random forest model. Random forest outperforms single decision tree by aggregating predictions for multiple trees, reducing the impact of noisy or overfit trees. Excel in generalization to unseen data, capturing complex patterns while mitigate overfitting. However, it's costly to implement and provide less interpretability as evidenced in wide range of features with large variations in the feature importance plot. ADA Boost performed the best while using only 7 variables. It combined prediction from weak learners to form a robust model. Coincidentally, the first 7 principal components from PCA explain about 90% of the data variance. The learning rate controls each learner influence, and smaller rates foster gradual learning, enhancing model generalization. Both XGBoost and Gradient Boost performance heavily depends on finding the right combination of hyperparameters. With a massive amount of hyperparameters, it is very challenging. The complexity in parameters tuning could have contributed to the suboptimum performance observed in the experiment. Next, we build a neural network model. The test accuracy with PCA is slightly lower. Difference likely due to the information loss during dimensionality reduction. PCA projects data onto lower dimensional space, potentially discard important features. Original feature space might offer more options for the neural network to select the optimum features. Let's move on to model comparison. ADA-Boost classifier have perfect accuracy of 100%, easiest to implement with a minimal parameter to tune. Random forest have second highest accuracy, but however it have very long computational time, minimal improvement in accuracy compared to other models. Third runner-up is tied between logistic regression, lasso classification, naive-based classifier, gradient boost, XGBoost, and neural network. We would prefer the lasso classifier or logistic regression based on the ease of implementation, and it is also computational efficiency and its interpretabilities. Other models not recommended due to specific reasons as follow. Gradient boost and XGBoost have too many parameters for tuning, its difficulty in finding best parameters. Neural network is computationally heavy, hard to interpret. KNN SVM classifier trees slightly lower accuracy compared to other models. To assess the effectiveness of the imputation, we choose to allocate 80 out of the 159 rows containing no NaN value to the test set. The remaining rows, along with those subject to imputation, will constitute the training set. Our objective is to evaluate whether our top 3 models, trained using 100% imputed data, can accurately predict the original entries without NaN values. To ensure data integrity and prevent leakage, we will use both the original raw dataset and the impute dataset. The findings suggest that imputed data significantly contribute to the development of highly accurate model. Remarkably, all 3 top models achieve 100% prediction accuracy. This underscores the effectiveness of imputation even when confronted with a substantial number of missing values in our experimental setup. However, it is crucial to acknowledge the limited data set size of 400 rows. Therefore, it's important to exercise caution when generalizing this result to larger datasets. Additional testing and validation are imperative for substantiate these findings. This concludes our presentation. Thank you for listening.